Hey everyone, welcome to Cleared For Takeoff. Cleared For Takeoff is a student-run interview series featuring aerospace professors, professionals, and students focused on sharing real experiences in research, academics, and industry. It aims to give high school students clear, practical insight into pathways and careers in aerospace engineering. Today, we have the pleasure of being joined by Dr. Bolei Deng, an assistant professor of aerospace engineering at Georgia Tech, whose research combines artificial intelligence with the design of mechanical metamaterials. Thanks so much for joining us today.
Yeah, of course, my pleasure.
For our first question, we saw that you grew up in China and you did your undergrad at Zhejiang University. Then you moved
Right.
to Harvard for your PhD and MIT for then you
Yeah.
moved to Harvard for your PhD and MIT for a postdoc. That's obviously a massive leap geographically and academically. So we were wondering, how is the culture and environment different at each of these places, and kind of what were your takeaways?
Yeah, I think the biggest leap would be when I graduate from Zhejiang University and went here. But fortunately for me, we had those program where in my senior year, I get a chance to do an intern. So my home school paid for that. And I went to Harvard to do that intern and end up get a PhD position at the same group I did intern.
Uh-huh.
So that's eased it a little bit because when I was an intern, um, I also need to do some coursework in my home university, so it's not like fully engaged. So I get some buffer. Um, but yeah, I would say the biggest difference would be um, I think would be how you approach. I think a couple of things happen at the same time. It's hard to decouple because from undergrad to graduate study is different, and
Uh-huh.
also from China to US is different. So I think if I would only to comment on the cultural difference is in US it seems much more independent,
Uh-huh.
and you have to do your own things a little bit more. You don't have classes and so on that you take with everyone else. You are more kind of more independent, and um, I actually don't feel very overwhelmed at that time. It was pretty smooth for me, especially. Yeah.
Thank you.
Okay, so for our second question, diving into your research sits at the intersection of AI, material science, and mechanical engineering. But
Right.
you're in an aerospace engineering department. How do those pieces all fit together, and how do you even describe what you do to somebody who's never even heard of metamaterial?
Yeah, so yeah, as you know, so about my background, I went to Harvard and I learned mechanical engineering, and I went to MIT where I did research on AI, and now I'm in aerospace engineering. So honestly, what I do now is closer to mechanical engineering, but fortunately, aerospace is like more like a application-driven part, so they don't care what knowledge you use. So a lot of my stuff actually have great application in aerospace. So that's how everything comes together. And speaking of metamaterial, it's kind of, I wish I have sample here I can show you guys, but I'm at my house. So I think an easy way to put that is for metamaterial, it's kind of like a structure
Uh-huh.
but with repeating structure. But the detail of the structure is so small. It's small compared to the application scale. So for example, if you have a rod that is 3 feet long, but every unit cell is like zero point 0.1 inch.
Uh-huh.
So speaking, when you look at the rod, you don't really see the unit cell. So the unit cell is some like a kind of a sculpture-like thing. And so that those sculpture, you can design the geometry of those small unit cells so that you can control the whole property of the rod. And nowadays, 3D printing really powerful. You can fabricate something very extraordinary. Um, and then the burden is actually how you design those unit cells. That's where the AI come from. And uh, and then the whole thing can be used in aerospace application for like impact absorption and so on. So now you can see that it's go all the way from mechanical engineering because you need to figure out how those unit cells affect the global property. And then there's AI help you to design those. And then finally aerospace is about application.
So
Yeah.
you're saying kind of like you learn the skills from like usage of AI and mechanical engineering and you apply that to like an aerospace field is what you're saying?
Yeah, yeah,
Okay.
that's pretty accurate summarized. Yes.
Thank you. So next question I had was metamaterials are closely related to semiconductor materials, which are increasingly more important today. What are your thoughts on the future of semiconductor related majors and skills in the future of society with AI use increasing?
Uh, I have to clarify the metamaterial I work on is called the mechanical metamaterial, and the one you refer to probably closer to optic metamaterial, which is makes sense because that's where the metamaterial originally comes from. They use that to control light and sometimes electronics. But
Mhm.
we are using that to control, if you may, like force bearing, load bearing, or impact property
Mm.
using the similar ideology, but methodology, but totally different application.
Mhm.
But on your question, I don't think I'm in the position to answer that, but I can share some of my thoughts.
Mhm.
Semiconductor, of course, very hot recently. Especially if you look at the stock market, you will know how crazy they are. And and I believe there is still strong need for AI in the near future. And I personally think it just starts.
Mhm.
Everything will be sort of substitute also by AI. So nowadays it's like almost like when computer first come out, uh, some people insist to do calculation by hand, but some people start to use computer. But nowadays, no one doing calculation by hand. Everyone use simulation. You probably also use writing code and so on. So
Mhm.
I think AI is kind of like the new tool everyone have to master, and it's really help you boost your working efficiency a lot.
Uh-huh.
Yeah, and as for semiconductor, it's a basic basis for AI for sure, and I think it's a very important industry because that's kind of it's kind of oil for AI, right? You need to
Mhm.
um you need to have the power to fabricate that. Yeah.
And
Thank you.
just a follow-up question
Yeah.
about AI. How do you see like the aeronautics and astronautics job industry and also just the engineering job industry? How do you see the increasing usage of AI kind of affecting that?
Yeah, if you look at the typical work by a engineering, I don't know too much about aerospace. I have to say. I probably know more about those CS major or people who do in design and uh, 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 mechanical engineering, that kind of stuff. Um, I don't know if you guys probably know nowadays you don't really need to write code by yourself. You write code in natural language now pretty much. I have friends work in big tech company. They tell me like when they work with AI, it's like they are the manager of a team, but they are like one man army.
Yeah.
Um, so that's totally changed how you work actually. You work mostly with AI those days in order to achieve very high productivity. So that will for sure change every industry. It's just a matter of time. And the better you learn to work with AI, the better you will be more adaptable to your job. And another note about the future of industry, I think, is you will not doing essentially the same job. You probably will change your job or change your um, even field every couple of years.
Uh-huh.
And then the ability to adapt to new role is more important in future.
Yeah.
Yeah.
Thank you.
Yeah.
And for our next question, you work on physical intelligence, which is the idea that materials that themselves can sense, compute, and make decisions without a brain or chip. That sounds like science fiction. So we were wondering how close to reality is it, and what could it actually mean for the engineering fields?
Yeah, I can give you two examples about that. It's not actually not science fiction because we have very concrete ideas about that. I
Uh,
can give you two examples. First example is very easy to understand. Um, we are trying to build those electronic free system because in space, electronics are pretty much vulnerable to a lot of things like temperature, radiation, or electromagnetic field. So if you can have a system that's completely free of electronics, it's going to be cheap to bring up, and it's going to be robust, and it's also it's also like in space station, you want to fabric new things, and you can use 3D printer to melt it and fabricate new things. So there's a couple of advantages. So what we did is very simple. Probably with high school knowledge, you can understand a bit of that. So we designed a system, a kind of like a structure where you have those little 3D printed pendulum. I don't know if you know the pendulum, depending on the length of the beam, you can have different resonance frequency.
Yeah.
There's a concept called the resonance frequency. Okay. And this is not something new. It's studied by like for probably a couple of 100 years. You can accurately control the resonance frequency by just changing the beam length a little bit during printing. Okay.
Are you saying
now, yeah,
like similar to like a metronome, kind of like how far or up and down you keep the dial?
Exactly.
Okay.
Yeah. So then what you can do is you can send a linear wave into the structure. That can be done by just adding some kind of vibration on one corner of the structure, and that vibration will propagate throughout the structure. And then those little pendulum will be activated only with certain frequency. So you can call those pendulums.
Oh, okay.
Right. So they have different resonance frequency. When you are not exciting at that frequency, they will not vibrate. Only when you, so then it's kind of like a mechanical phone call. You can call each part. And then we have a way to transfer this vibration into some function. For example, the two parts detach or like a locomotion move around. Everything is controlled by this wave. You just modulate the frequency.
Okay.
So that's sort of I give you an idea what physical intelligence means. There's no electronics here, but you can somehow send signal to different part of the structure. Yeah. Another example, I think it's probably more interesting that I think the essence of physical intelligence is it's kind of like the body of a robot need to work with its brain cohesively. In biological system, body and brain are evolved together. The way body collect data from the external environment is optimized for brain as well. So give you a more concrete example is we can design a robot which can sense the external environment. For example, if something hit it, it can sense it better with a more carefully designed metamaterial body.
Yeah.
So and it can work with the brain, which is maybe a computer chip inside, to make the burden on brain reduced or the overall performance higher. Yeah, that's kind of like the two examples on top of my head.
Thank you.
Yeah.
So I had a question. A lot of high schoolers are drawn to aerospace, imagining they'll be designing rockets or planes. Your work is more about fundamental and novel materials those vehicles are based on and built from. What would you say to a student who is interested in aerospace but doesn't see themselves fitting to the traditional mold of a like rocket scientist?
Depending on why you are interested in aerospace, right? I think I would say you should look at the courses the program offer and see if those courses are interested to you. Because after all, major is just a name. Your capability is trained through those coursework and the curriculum.
Yeah.
If you are not interested in, for example, I think like combustion, fluid dynamics, then mechanical engineering probably fits more. Because I think in aerospace, you need to learn a lot of fluid related thing as well. Yeah, but I think again, it's all about the curriculum you take. I don't think I fit to aerospace very well, but my work have a lot of aerospace application. So also I would say look at the industry you want to go into, what kind of job you want to do. Do you want to do academia job or industry job? If it's industry job, what is your dream job and what that requires? And does the curriculum in this major really satisfy that? Yeah.
I had a follow-up question. How did you through like out your academic career, how did you find that you wanted to do like metamaterials?
Mm. It's actually very simple because my PhD advisor did that.
Mm,
It's as simple as that. And I did not have a choice in the beginning, but then I feel it's a very intrinsic, a very intriguing idea to work on,
mhm,
um, because it combines. Because I majored in mechanics before. I like mechanics,
mhm,
and but the mechanics, is a very old subject, and people are studying a lot of very ancient topic. But mathematics really kind of like bridging computational AI with mechanics, because now it's all of a sudden transformed the boring mechanics problem into some sort of design problem, optimization problem,
mhm.
because the design space is so rich. So I was really intrigued by that, and so that when I went to MIT, I studied computational science and artificial intelligence to better do this, and yeah, then I get very interested in this.
Thank you.
Yeah.
Okay, so for our next question, going back to your research, your lab published a paper in Nature about microstructures that move and self-regulate on their own
Yeah.
onto liquid with no motors and no programming. How
Yeah.
does a material decide to move, and what does that really look like up close?
Yeah. It's actually, I don't know if you see the movie in that, but if not, that's okay. It's actually a very, very cool idea. Um, Yeah, just more explanation for the audience who don't know. We have a way that so there is some microstructure like a lattice, triangular lattice. Their size are very small. You cannot see that. So within 1 millimeter. So millimeter is like 1/25th of an inch. So within 1 millimeter, there are 10 unit cells. So you cannot even see each one of them. So it's very, very small. Probably like the thickness of your hair, each unit cell, like a triangle. What we did is we add a droplet of liquid, and the liquid is acetone. So acetone is something evaporates very fast. So we add a droplet, and then after the acetone evaporates, we use a microscopic to observe again. It becomes a triangular, it becomes a hexagonal lattice. So everything changes, which is very intriguing. And you should see the video of that as well. And it happens in real time, it's like a few seconds, it transforms happens. So how did that happen is we actually use capillary force. So capillarity when you wash your hair and after it's not dry yet, you will see your hair actually go, especially for people with longer hair, they collapse into bundles, right? Small bundles. This is because whenever you have some kind of two surface, there will be a meniscus form, the water meniscus form on the two hair, because your hairs are so soft, so they are merged together. Okay. Normally, this capillary force, you also saw that in straw. If you have a cup of coffee or something, you put a straw inside, you will see the capillary force trying to lift the surface a little bit higher. Okay. Normally, they did nothing because they're so weak. Okay. But what's smart in that paper is it is weak in large scale, but in microscopic scale, it's not weak. So when you make your structure micrometer scale, when it evaporates, the meniscus will naturally form on every corner of the triangle. And at that scale, this force is large enough to deform the structure. So actually, they zip the triangle together, and then it's transformed into a different lattice. Um, so the cool thing is that when we are not like moving everyone one by one, we just let capillary like meniscus naturally form. It will form on all the corners, and then this just drives the assembly of the structure. Yeah.
Thank you. For our next question, you use AI to discover new metamaterial designs, but AI in most people's minds means ChatGPT or image generation. So what
Uh,
does AI actually look like as a scientific tool in your lab? And what can it find that a human researcher just couldn't?
Yeah, good question. So for what we use, we do not actually use a large language model, although we could, but that's more convoluted. The simplest, I can give you a simplest example. Um, okay, so normally when we do what inverse design or optimization means is you have a design space, right? You have a shape space, let's say, and you can have all different shape, right?
Hmm.
Each shape will corresponding to a property. So let's say you design a certain shape of unit cell, you design metamaterial, you can compress it. You can measure its stiffness, right? So every shape will map to a stiffness. That's simple. That's called forward problem. You can run simulation to do that. You can run finite element or ABAC simulation if you heard of that. But that's called forward simulation. What inverse design means is I want this specific stiffness, not higher, not lower. Find the design for me. Okay. So what would you do? Normally you would give a lot of guess, like let me guess this one, let me guess this one, and check the steepness. Okay. That's kind of like a more like a random search. But there is different algorithm you might heard of, like Bayesian optimization, gradient-based optimization, Newton's method. They all do one thing. They use the simulation tool you have, shape to property, and try different shape and find the correct property. Okay, but there's one problem is that, especially in metamaterial design, the simulation process takes a long time.
Uh-huh.
And as you can imagine, if you are just randomly trying those options, it's very hard to find what you want. And the stiffness is very simple property. You could be looking at, for example, stress strain curve, which means the whole history of compression. So that's actually more convoluted property. That means it's even harder to find. So what we did is we need a faster simulator, but it's not trivial. So then we just did something end to end. That is, we train a neural network from the shape of the geometry to property.
Uh-huh.
It needs some training data, but then once it's trained, it's super fast. And if it's super fast, then you can do this search much faster. So this is the example of how AI is used. So in this case, as simple as a neural network. And for fancier ones, we also use generative AI to generate the shape, and you also need some training data. But there is a trade-off. That is, the less physical intuition you give it, that means you just brute forcefully train it. You could do that, but then you need much more training data, which at some point will become impossible. But the more physical knowledge you add to your AI model, the less training data you need. So that becomes more and more powerful. So there is a trade-off still.
So would it be like correct me if I'm wrong, but is it like kind of like training like a small language model, are you saying, or with like a lots of data specific to the problem?
It's something like that, yeah. So the
Okay.
better your data is, and so yeah, that's a great example. So how to choose the data you use to train will make the training very different. But how to choose that will be based on your physical understanding of the system.
Uh-huh.
Yeah,
Okay. Thank you.
yeah.
So for our next question, we were wondering, what is something you wish someone had told you when you were 16 or 17 about what a career in engineering research actually looks like from day to day, and what the rough parts are as well about it?
Um, um, that's an interesting question. I was discussing with the undergrads at GT just yesterday. Um, he told me he feel like he's I think 20 now, and I'm in my 30s. I'm 32, and he thinks like in a blink of eye, then you will see 10 years pass and 20 years pass. You don't even know what happened. But then I tell him, I think it's applied to this answer as well. There's no need to look back or look forward, because you will be a complete different person
Yeah.
when you like. So for example, for me, I'm completely different. I mean, everything like perspective, understanding of the world, very different from 16. I could tell me a 16-year-old something, but probably I choose to tell nothing, because nothing is relevant even. because the way you look at the world will change so much. And if I forcefully put how I understand this world to 16-year-old me, it's probably won't work at all. So I would not think too much about future and do just I would just look into a few years into the future, but not like 10 years, 20 years, because too many things can change in this period, and there's no need to overthinking at all. Just do what you want to do now.
Thank
Yeah.
you.
All right. If a student watching this genuinely was curious about metamaterials and AI driven design, what's one concrete thing that they could do this week to start exploring it and maybe, like get into it for their major or for a PhD in the future?
Good question. I think as for now, so I want to clarify, metamaterial will not be covered in any of your undergraduate class
Hmm.
because it's a little bit, it's not some basic idea. So anything you wish to understand now probably will feel quite different after you learn all the required classes. So I would just, so in order to get an idea, I think the best way is to ask ChatGPT to explain that to you. Instead of looking for papers, uh, you will not feel very comfortable for the papers you look at because they're
Hmm.
probably too hard for you to understand. I would just start with ChatGPT and ask what is metamaterial, what is fun about that, and what is the opportunity it can give, and maybe ask it to point you to some videos. I think in the early stage, always look at pictures, videos, or communicate with ChatGPT. Once you think you get an idea, you have the interest, then you start to look at papers.
Okay.
Yeah.
Thank you.
So I had a follow-up question. When you were getting into metamaterials, did you find it difficult at first? And how was that experience like?
Um, yeah, I find it's quite weird in the beginning because the way they studied it's very computationally expensive. So give you some background. When I first studied this, everyone only look at how wave propagate in metamaterial, linear wave, like small amplitude sound wave propagating there. So in order to do that, you need to do some complex eigenvalue analyze. You all know what that means after you learned linear algebra. Um, and then you will, the only thing people care is at what frequency the sound cannot pass that, so that they are using some kind of sound blocking system. And uh, at that time, that was 2016, people are crazy about the idea that the shape can change the, we call that band gap. Band gap means the range of frequency that cannot pass.
Mhm.
So they just try different geometry and publish paper. And I find it pretty boring at that point. So but then I quickly find something interesting is large amplitude impulse. If the impulse is becomes large, it's so large that even change the geometry of the metamaterial, what will happen? And I take a different path. I build a uh, simplified model. So my model is much simpler than other people's model. Although it's simple, but I get the key idea of what I want to model. So it's also worked. So then that's when I start to use my own approach to study everything there. Yeah.
Thank you. And I also had one more follow-up question. So this is kind of, I'm not sure if you work in this section, but I know for like metamaterials, there's like a large topic of research is kind of like super hydrophobic surfaces and avoiding like water buildup on surfaces. I was wondering if that intersects with any of the work you do.
Yeah. Uh, the the liquid induced transformation of microstructure, that thing actually have some application on that because when it's triangular lattice, we find is attracts water, but when it becomes hexagon, it becomes water phobic.
Yeah.
So you could use a droplet to change the water surface property on that. Yeah. Yeah.
Thank you. Yash, Alex, did you guys have anything else?
No.
Thank you so much for your time. We really appreciate
Yeah,
you.
of
Yeah.
course.